This is part 5 of the calculus section of our aeronautical engineering course. In part 4, we determined that the bending moment contribution of this top 1/8 inch sliver was 2,093 inch-pounds. That's for the top sliver. We determined that the next highest sliver's bending moment contribution was 1,831 inch-pounds. And we figure the bending moment contribution of each of these other slivers in the same manner. We take the area of the sliver, which is the same for all of them. They're all 2 inches wide by 1/8 inch high, which gives us a 1/4 square inch area. So the area of any given sliver times, like, let's look at this sliver, okay, between that line and that line. Okay, it's the same old 2 inches wide by 1/8 inch high, 1/4 of a square inch. The area times the stress in the sliver Now the maximum stress was 4460 up here at the top of the board, and a 0 in the middle. And the closer you get to the middle, the less the stress is. So we draw us a line here out of the middle of this sliver, and that distance between there and the centroid, divided by the distance from the top of the board to the centroid, gives us our factor to multiply the maximum stress by to obtain our stress in the sliver. So we have area times stress in the sliver. That gives us the force of this sliver. And we take this distance again, the distance between the sliver and the middle, and that gives us our arm, our distance between there and the center. Force times distance gives us a bending moment contribution. So let's just say distance to centroid. So it's the same old formula, almost. And if you'll work them out, if you're not sure how, go back and look at part 4 and see how we got that 2,093 and that 1831. And feel free to work them all out. The highest is that, the next highest is that, and the remaining 14 are 1588 for that one, 1361 for this one, 1152 for this one, 960 for this one, 786 for that one, 629 for this one. Notice they keep getting less and less. 490 for the shaded in one that we just talked about. 368 for that one. Notice the top and bottom of this board do a lot more contributing to the strength of it than the slivers toward the middle. See, 264, 176, 107, 54. They're getting pretty wimpy here toward the center. 20, and this one right close to the center is only 2 inch-pounds of bending moment contribution. When you add up all these numbers, 2,093, 1831, 15, whatever that was, 88, yeah, all these numbers, you'll get 11,000. Let's see, where'd it go? 881 inch-pounds. All these bending moment contributions, but bear in mind that's just half the board that we looked at. If half the board is in tension, the other bottom half is in compression. Whatever the top half is contributing to the bending moment, the bottom half is contributing an equal amount. It's kind of like if here's a board and one person's pushing at the top part, another person's pulling at the bottom part. Well, we just figured the top part, so we figure the bottom part too and add them together. So that'll give us 23,762 inch-pounds of bending moment. Okay, if you've forgotten what we're talking about with bending moment, well, let's say this is our 2x4 board, and here's a fulcrum, and it's a teeter-totter, and here's a guy sitting on this end. Here's a guy sitting on this end. Okay, let's say this guy weighs 100 pounds. Let's say he's 5 feet from the fulcrum. Well, 100 pounds times 5 feet is 500 foot-pounds of bending moment that he's causing at the fulcrum. That's where the greatest bending moment is, right there at the fulcrum. And 500 foot-pounds is going to be 500 times 12, which is be 6,000 inch-pounds. Isn't that what you get when you multiply 500 times 12? Yeah, 500 times 10 is 5,000. Yep, 6,000 inch-pounds. So this board, we've calculated that it should be able to withstand over 23,000 inch-pounds of bending moment. As long as it stood on edge, you turn it over flat and it won't be as much. But we'll get around to figuring that stuff out later. This bending moment of 23,762 inch-pounds that we calculated sliver by sliver, it's not an exact answer. The exact answer can be found by calculating the section modulus, which we use the letter Z to represent the section modulus. Okay, we calculate this section modulus and we multiply it times the stress. In other words, M is the bending moment equals stress times section modulus. And I'll go ahead and tell you the formula for section modulus for a rectangular cross-section beam. We'll derive this formula later on in this lesson using calculus. But this section modulus equals base times height squared over 6. That's the formula for a rectangular cross-section beam. So if we want to see what our bending moment is, we say M equals, this S is maximum stress there at the top, which was 4460 pounds per square inch. And section modulus is base times height squared over 6, which was, the base is 2 inches. Okay. Height was 4 inches. You take it of the whole beam, 2 by 4. 4 inches, and all that's squared over 6. Well, 2 inches times 4 inches times 4 inches is 2 times 16 inches. Actually, inches cubed. 2 times 16 is 32. It's 32 over 6 equals 5.333 forever and ever inches cubed. That's what our section modulus is. So our bending moment is the stress times the section modulus. So that times 5.333 inches cubed. Okay, pounds per square inch times inches cubed. So that gives us bending moment equals 23,787 inch-pounds. Notice how close it is to our 23,762. that we estimated, figuring it sliver by sliver. Now we're going to use calculus to determine the bending moment of our 2x4 board. We'll integrate an infinite number of slivers. See, I drew a little sliver here. That one's not 1/8 of an inch high like the ones we did using the non-calculus method. This is infinitely thin, and we have an infinite number of them, and the thickness of them approaches 0. Okay, each sliver has a width of W, which is same old 2 inches, and a height of DH. See right there, DH. That's the distance between the bottom of that sliver and the top of that sliver. Of course, it's almost 0. It is 0 when you have an infinite number of them. Okay, the area of each sliver is, we'll call it dA, which is the area of this little sliver. It's equal to W times DH, 2 inches times DH. Okay, when using calculus, anytime you see a lowercase d like that and some other letter next to it, think a little sliver of whatever this is next to it. This dA, that's the area of our infinitely thin sliver. So dA is a little sliver of this infinitely thin, well, infinitely small area, but whatever that area is the width of here times DH. So DH is a little sliver of height. Okay, let's let dm be a little increment of bending moment that's attributed to our sliver of wood. So dm equals the area of our sliver which is dA, times the stress in our sliver, okay, not the maximum stress at the top of the board or the 0 stress at the middle. It'd be the stress in the sliver, wherever, depending on where it is between the top and the middle. Okay, times the moment arm, that distance from there to there, which is h, times the moment arm. Yeah, running out of room here, aren't we? Could have just written h there instead, because that's what the moment arm is between our sliver and our centroid. But yeah, we won't really get into this right now. We'll save the rest of this math for next lesson. See you then.